that working now? Okay. Okay, so sorry about the delay. The talk today will be about a couple of things: parameter estimation for gravitational wave data analysis, mostly for LIGO applications, which is where I work, or where I do most of my work, and I do that work on parameter estimation mostly. So hopefully I'll get some questions. I haven't really tried to go through every single little detail about the particular case of LIGO, but I wanted to more focus on how parameter estimation actually works. And I'll show you some examples from Lisa as well, not from pulsar timing arrays, because I haven't looked at that myself, but I think Stephen will be able to field questions on specifics of that case. But especially for the students, I wanted to give a bit of background as well, because I think the idea of doing data analysis in this way is something that's caught on more over the last kind of 15 or 20 years. So we'll start off fairly gently and then talk about some of the methods that we use. So let's start by looking at Bayesian inference and then different gravitational wave analyses that we've worked on using these methods, mostly parameter estimation, but I'll briefly mention model selection as well. And then the algorithms that we use fall into this category called stochastic sampling, which is in the title of the talk. That's a kind of quite a broad range of techniques, and there are two in particular that we use a lot. They're quite difficult to get them to work well, so there's a lot of tricks involved in doing it. And so at the last bit, I'll go through a few of those tricks, so you have a sort of idea of how people come up with these things. And that, final area is still very much being worked on, especially by statisticians, so they come up with new algorithms all the time, and we have to test them out on different problems. So there can be, some of them are good, some of them aren't so good, some of them might work on your problem, but not on a different problem, and so on. So this is the kind of thing I'm talking about when I mention parameter estimation. So hopefully you've all seen the detection paper for GW15914, and you'll have seen there are plots in the detection paper and in companion papers that look something like this. These are a sample of different results from that first detection. You can see the masses, the spin parameters, and the sky localization being some of the most interesting ones, for example. I should use the pointer. But do you know what we're looking at when we plot these things? I mean, you probably understand that sort of related to where we think the true parameters of the source are. But these are probability distributions, basically. So what you're looking at is a two-dimensional projection of a high-dimensional probability distribution. And what we do is we simultaneously ask the question, what are the parameters of the source? Primarily, that's what we're interested in. But there's a lot of other things that we don't know when we're doing our analysis, and that can make things more complicated. For example, we don't know exactly how the detector is calibrated. So we have to include a model that allows the calibration of the detector to vary as a function of frequency. And that has 20 more parameters per detector. So when we're analyzing these sources, you might think, well, we just care about the source, but we actually, in order to encapsulate all the uncertainty in our model, we have to give lots more parameters. And each of those parameters is a dimension in parameter space. And so the title of the talk, or the title of the session, was Efficient Sampling of High-Dimensional Parameter Spaces. High-dimensional is a very loaded term in stats, and depending on your favorite algorithm, you might say it's like 10 dimensions, or you might say it's 1,000 dimensions. the cases that we do in LIGO are between around 15 to 50 dimensions. The cases in the PTA that Stephen mentioned yesterday, I think you said it was several hundred. So that sounds even more complicated. So I'm interested to know whether the sort of things that we use would scale to that problem and what kind of tricks you're using as well. So when we get into the sort of technical details of the tricks, then we can open it up to other people's expertise as well. Okay, so let me go back, way back, to look at some history, just for the benefit of those who are new to this. So this probability business, yeah. Yep. So the function, the probability function, is not discontinuous. It's defined on the entire sphere. And these probabilities contours, the first one is the smallest area that encloses 50% of the probability. And the second one is the smallest area that includes 90% of the probability. And it just happens that part of it is here and part of it is here. So if I was to say ignore that and go here instead, I would have to circle more area than I would. So it's like you take the smallest area that encloses 90% of the probability, and there's no reason that has to be contiguous. Your probability distribution in general will have a weird shape that has lots of little lumps and bumps. I can draw it. I actually have a slide that has the antenna pattern on it, but I didn't include it. I can, well, okay, it doesn't matter. Maybe I will, actually. This is it's supposed to be an interactive thing, isn't it? There it is, right there. For LIGO and for all of these interferometric detectors, the antenna pattern actually is very broad. So although there are points that it's not sensitive, it can detect signals from all over the sky, more or less. It's just differentially sensitive. Antenna patterns in general is quite an interesting topic, but you know, you have probably studied at some point a parabolic satellite dish, which has a receiver here, and it has another antenna pattern of its own that's very directional. So for a satellite dish, the antenna pattern has a very strong central peak and then a couple of side lobes. And it goes to 0. So you can only, it's very focused. That's why you have to angle it on the sky, and why you have directional sensitivity for satellites and radio telescopes and stuff. For gravitational wave detectors, because you can't screen gravity, you have to be visible to the whole sky. And that's just the type of pattern that we get. Anyway, digression. I'll talk about time delays, and this ring business is one of the things that we have to use, one of our tricks to solve. Well, we don't have to, but it helps. It's a place where we can make it more efficient. So remind me when we get to efficiency improvements to bring that up. Yeah. Okay. Let me go back. Right, probabilities. I want to just go very quickly through this because you may know that probabilities is like if I do an experiment many times and I get outcome A 50% of the time and outcome B 50% of the time, then I would say there's a 50% probability of A and a 50% probability of B. That's not what we're talking about here. We're talking about a different method, a different interpretation of probability. And it was actually the original interpretation of probability. So when you hear people talking about Bayesian inference or Bayesian probability theory, we're talking about this version of probability that was invented by this guy called the Reverend Thomas Bayes back in the 1700s. And it was actually the first scientific investigation of how you can know things like about random experiments. So he wrote down these rules. He didn't really use them very much apart from for gambling, which of course is still what we use it for mostly. But then later on Laplace, who's of course a titan, derived dozens and dozens of results that are still used these days. In particular, he discovered this universal nature of Gaussian distributions. So the Gaussian process that we talked about yesterday is a generalization of this Gaussian distribution that just crops up absolutely everywhere. And there's a reason for that, because it's kind of like a eigenfunction of lots of different transformations that you can do. And things, once they get to become Gaussian, they tend to stay Gaussian. So it's a very useful distribution to use. So that was the norm in science for most of the 19th century. And Laplace and others used it to do astronomical inference in particular. So what we're doing these days is directly inheriting what was done 200 years ago. In the 20th century, things took a bit of a turn, and the sort of professional field of statistics was invented, mostly to deal with biology and things like that, where you really do have these repeated trials. So people started thinking about how often a gene is expressed, or how often a particular, someone's eyes are a certain color rather than another one. So they started thinking of probability in terms of the frequency of occurrence of things, and that's called frequentist statistics. So frequentist statistics is a sort of special case of the Bayesian inference that's applied to particular cases. You can also derive all these things from first principles. So when it was, there was always a sort of underground group of astronomers in particular who kept the old version of probability going. And later in the 20th century, people showed it could be derived from some simple axioms, that it is in fact the unique theory of probability. And so, if you believe in logic, it's an extension of logic to things that are not either true or false, to something that can be true or false with a 50% probability or 20% probability of being true. It's the only way to self-consistently describe a theory of that type. Unfortunately, to do it properly, you need to do a lot of integration. So this was another reason it sort of fell out of fashion, is because a lot of the problems that you'd like to apply it to are quite intractable on paper. So it wasn't until people started doing numerical simulations on computers and doing numerical integration that way that this really took off again. So since the kind of turn of the millennium, this has had a heavy resurrection in astronomy and other parts of physics, and in other fields as well. I mean, machine learning and all of this stuff as well is kind of part of this same boom in different techniques about trying to learn things. So it's definitely now, I think, dominant in astronomy, and you will almost certainly hear about Bayesian inference at some point in your career if you're ever, interacting with data a lot. Okay, so all of my talk is in the context of Bayesian inference. So just so you understand what that means. In particular, what was advantageous about Bayesian inference is that if you're a frequentist, then you're perfectly happy to say that if I roll a dice and I can predict that I will get a 1/6 of the time, or something like that, I can say I've got an experiment, I can predict the outcome. So that's called sort of forward probability. It says I've got a model, I can predict what the data is going to look like. But it doesn't allow you to go backwards and say, I've got some data, what does it tell me about my model? And of course, the situation that we're in science all the time is that situation. Like, we've done an experiment, we've got some theory, and we want to know what the data tells us about the theory. So we have to do this inverse probability thing that you need Bayesian inference in order to do. So how do you do that? How do you go backwards instead of forwards? Well, that's where Bayes' theorem comes in, which I think you've probably heard mentioned many times already this week. This gives us a way of updating our beliefs about a model, theory, for example, given some new information from an experiment or from an observation or any other kind of information, say that you heard somebody telling you something. And all it does is a very simple derivation. If it start from the joint, the rule of joint probabilities. This means the probability of A and B being true at the same time. You can write that in two ways. It's the probability of A assuming that B is true times the probability of B, and that's equal to the probability of B assuming A is true times the probability of A. And of course, just by rearranging this equation, equal to the probability of A given B times the probability of B divided by the probability of A. Okay, that's Bayes' theorem. For some reason, this is enormously controversial. It seems totally straightforward to me. Anyway, that's how you go. So this is the frequentist bit. It says I have a theory. I can write down the probability of getting some data. So that's the forward probability, making a prediction. And this is the backward probability bit. So I've got some data. What's my updated probability on the theory? And when it's really interesting, I find it fascinating. It's basically a mathematical theory of learning. It's very general, and you can tell your computer how to do it, most importantly. So these things have names that are jargon, but I will use the jargon just because it's hardwired into my brain now. So this is called the posterior probability. That means it's after you've done the experiment, so it's posterior to having done the experiment. Prior, likewise, means it's what you thought before you did the experiment. That's the likelihood. It's typically the forward probability part. And at the bottom, you've got what's called the evidence, which is a bit of a silly name, but it's very commonly used. More descriptive name is the marginal likelihood, which is the probability that you'll get this new data under any of the theories, if you know what I mean. So you integrate over all the possible theories. Okay. Questions about Bayesian in general? Is that clear enough? Okay. So then let's go on to LIGO. This is mostly my bread and butter. We can start talking some details. So we see again the recurrence of this Gaussian distribution here. So what we know about LIGO data is that it has some particular power spectrum or power spectral density. And as we said yesterday, it's all related to this Gaussian distribution. So we know two things about the LIGO data, ignoring for a minute the fact that there are glitches. One, that the mean of the data is 0, because if it wasn't, then we would see an increasing gravitational field all the time, which is something that experimentally isn't true. And secondly, that it has a known variance as a function of frequency that's given by this power spectral density function. So if you know these two things, then you have two pieces of information about your data. Then you can write down the unique probability distribution that describes that, which is the Gaussian. Of course, lots of things are. And it has that form. So under an additional assumption, that's for a single frequency bin. Then for the assumption that each frequency bin is independent, then you can write down the joint probability of all of the data in all of the frequency bins. It's just the product of the likelihood in each frequency bin. And because that product is of exponentials, that just gets converted into the sum over frequency bins inside an exponential. I don't need to write that down. Likewise, if you assume that the noise in each of the detectors, this Hanford, Livingston, and Virgo is independent, then you also have that the joint probability of the data in all of the detectors, given their own noise curves, is just the product of the individual probabilities, well, the likelihoods for each of the detectors. Is that clear? Okay. So something that we talked about yesterday, I don't know if we want to get into this, but the relationship between this power spectrum and the Gaussian distribution is on the fact that the frequency bins are independent, and that's true in the limit of like infinite stretches of data, because it's the orthogonality of different frequency bins when integrated over time that makes them independent. So you know that there are orthogonal set of basis functions that you can decompose the data onto. More generally, you can have a non-diagonal covariance matrix, in which case it wouldn't just be the power spectrum, but higher moments. So the power spectrum is the expectation of xi and xj. And if it's diagonal, it means that this is equal to sigma squared when I equals j, and is equal to 0 when I is not equal to j. But you can have other cases where the off-diagonal elements are not 0. Okay, so that gives us this likelihood function that I mentioned a minute ago. And that tells us, you know, what we do the experiment, we run LIGO. That tells us our prediction for what the data will look like. What the noise will look like. But we can have also a signal in the noise. And then we start getting to things that we're interested in, the signal parameters. So we know that the LIGO data is the superposition. It's just the sum of some gravitational wave signal h and some noise n. And now instead of the mean being 0, the mean of this likelihood function just becomes the predicted value of the gravitational wave at each frequency bin. But the variance remains the same. So if you put all that together, then you get a joint probability of the noise and the parameters of the signal. So theta is the parameters of the signal and the data, and you can decompose this in different ways. What we're actually interested in is the posterior probability of the signal parameters given the data. And so you just write down these things here. This in particular, again, is the likelihood function. Wait, that's actually wrong. I made a mistake in my slide. Oh dear. The variance. Yeah. But okay, the slide's wrong. Anyway, that's just supposed to be Bayes' theorem. I'll skip these extra pieces of information, these symbols, sigma and HS. So we want the posterior probability on the parameters given the data is the likelihood of the data given the parameters times the prior on the parameters divided by the likelihood of the data. So the marginal likelihood or evidence. So that evidence here is, in the case of these probability density functions, it's a normalizing constant. That means that when you integrate over all of parameter space, it sums to 1. More generally, it can be a number that you can compare different models. So if you have different models that you want to compare, then you calculate this number here under a certain model, and you calculate it under a different model, and then the ratio of these things will tell you the relative probability of the models. So it's a way of doing model selection that I'll talk about a little bit later. Okay? Questions? All right, so what does our signal model actually look like? This is an example of a gravitational wave from a binary neutron star. So it's quite long, much longer than the binary black hole ones that we have. And you can see that there's this characteristic chirp shape. So it's rising in amplitude and in frequency as a function of time. But more importantly, there's a sort of modulation of the wave, both in terms of frequency and in terms of amplitude. And that modulation is caused by the physics of the source. So how the source is rotating relative to the observer. The speed of the chirp is proportional to the mass and so on. And the spin effects, the dynamics of the spins can modulate the phase evolution. So there's a lot of information encoded into this signal. Information about the masses, the spins, the position, orientation, and time, things that I showed you on the first slide. In the case of neutron stars as well, we've got things like the tidal deformation of the stars, any kind of disruption towards the end, and if there's anything after the signal remains. We also, in the case of black holes, have the ring down as well, of course, which I didn't mention here. The question is, how do we get that information out? Yeah? These are the same waveform as it's observed in 3 different detectors, Hanford, Livingston, and Virgo. Here. So that is Livingston, I think. What's happening here is that this binary has some significant spin, and specifically spin that's not aligned with the orbit. And when that happens, no, I'm not that tall. When that happens, so say I've got the 2 stars going around each other like so, then you've got your orbital angular momentum vector here. But let's say that this one has a spin vector there. Then the total angular momentum of the system is going to be somewhere, I don't know, here-ish, which is usually labeled with J. And normally, so if there's no spin, then this is a conserved vector, and the binary just coalesces. The plane stays the same. But there's interaction between this angular momentum in spin and this angular momentum in the orbit. That means that the angular momentum moves back and forth between one and the other as the 2 things are coupled in the inspiral. And what's conserved, roughly, is this total angular momentum vector J. So this this vector of the orbit, it precesses around J, and as it does so, the direction of this orbital plane, it moves in and out of, well, at some point you might see it like that, another point you might see it like that, and then you might see it like that. See what I mean? So edge on or face on. And when that happens, you get different parts, H plus and H cross, coming out of the signal. So here you have both plus and cross. Here, okay, if I say that that's just one of them is plus, and here I'm back to plus and cross. And if the detector happens to be lined up so that it only sees one of the polarizations, but it's just a superposition of the two of them, then as this relative weight in the plus and the cross changes over the orbit, then the detector might see the amplitude being modulated because you only pick up part of the signal in each of the detectors. And it depends where it is on the sky and relative to the network as well. So it's more unusual that it's only in Livingston because that's basically aligned with Hanford. I don't know how I produced this particular one. Yeah, no, there is amplitude modulation in all of them. It's more common that Virgo sees something different because Virgo is not aligned with Hanford. Yeah, but it is definitely the green one that's getting modulated. So it must be at a very special place. I might have even specifically chosen it to illustrate that effect because I made that thing years ago. Yeah, probably. It could be a black hole in the neutron star. Anything else? Okay, so I already talked about what parameters there are. The other thing, okay, this is basically what I was trying to explain a minute ago. So the amplitude that you see is a function both of the amplitude in each of the polarizations and the detector response function to the two polarizations. So they each get, you know, oh yeah. Yeah, yeah. Yeah, I left that in there from other talks, but it's interesting in its own right. So Ricardo mentioned this Shannon entropy yesterday. Does anyone know what that is? Shannon entropy. Is it familiar? So this also is sort of is information, right? I mean, it seems obvious, but you can quantify it as well. I have a computer that has 500 gigabytes of hard disk space in it, so I can quantify information that way. But what does it really mean? Well, the basic unit of information is the bit, and that is the amount of information that you need to answer one yes or no question, because there's two states, yes or no. Okay? So let's consider a discrete case, first of all. Say I had an experiment that had 16 possible outcomes, and they were all equally likely. Then the amount of information I need to choose between one of the 16 outcomes is the log to the base 2 of the number of possibilities. Okay, so the log to the base 2 of 16 is 4, I think. So the information is usually written H is 4. bits. So this formula is the Shannon entropy, basically. This is a simple case where it's kind of uniform possibilities of each outcome. You can generalize that to cases where one of the outcomes is more likely than another, and then you get the sum over the outcomes of your probability of that outcome times the log of that probability. Forgot minus sign. Yeah, there's always a question of this minus sign. Yeah, but this if this is 16, then this is wrong. Oh no, this is 4 bits, but then this is the definition of entropy, not information. So for information, it's got the minus sign. Entropy is basically the opposite of information, so you'll sometimes see it written like that. Anyway, so that's for the discrete case, and you can then generalize that even further to the continuous case just by replacing the sum with an integral. It becomes a little bit complicated because then you have a measure instead of a probability distribution. So you have an integral over some x parameter where this is defined with the measure. Okay, so when that's maybe the information content in a particular probability distribution. So just to give you an intuitive idea of what that means, this distribution has very low information in it because everything's equally probable, and if you do this sum, you'll see that it's maximized when all the outcomes are equally probable. If I instead have this distribution, that has a lot of information in it because it says that it's probably one thing. That's information. It says it's going to be there. And you can see that when one of these outcomes is 1 and all the others are 0, then this is maximized instead. Now I can also write down relative information. So in this case, I'm comparing the comparing 2 different distributions, like that. And that is telling me how much I learn when I go from one distribution to another. So when I go from the prior distribution to a posterior distribution, by gathering information from an experiment, that tells me how much information is in the experiment. Is this novel or interesting, or just confusing? Anyway, any further comment? Yeah. It's very nice. I'm kind of a big fan of this stuff. You can derive huge chunks of thermodynamics just from this. And basically no physics even. Like it's all about your ignorance of what's going on. Like you're averaging over states in a gas, for example. You don't really need to know anything about the molecules. You just need to know how little you know about it, if you know what I mean. Yeah. What's the name of the author? Palin? Like that? E? Bailey. Okay, you can look it up. I would be curious to have a look at that. It sort of explains why this problem is hard as well. Because we're talking about distributions that have 30 bits of information in them. That means that, well, okay, if this is 30, then what is n? It's 2 to the 30. And this is a very large number. Well, it's quite a large number. So basically, the problem that we're trying to solve is finding one outcome amongst 2 to the 30 possibilities. And so, you know, you might want to say, I'll look at every single possibility, and each of them might have a cost to do that. And of course, that cost then gets very high overall if you do 2 to the 30 different trials. So the problem of doing parameter estimation and model selection is trying to overcome that, you know, exponential in the amount of information. Yeah, exactly. So, what, the integral? Well, it's the integral over the parameter space. Yeah. Yeah, the template bank as well. You can derive the metric on the template bank that was talked about as well from the same principles. But I'm not going to do that right now. I have a slide on it. I should have put more into this talk. Anyway, okay, so the other thing I want to mention before we move on is model selection. So I did say that you can compare the probability of 2 different theories to find out which one of them is true. And again, that's all doable within this framework of Bayesian inference. So in our case, it might be whether you want to know there's a signal or if there's just noise. And so you would want to compare the probability of the signal model over the probability of the noise model. And you do that by taking the ratio. And you have the ratio of the posterior probabilities is just the ratio of the prior probabilities times the ratio of this marginal likelihood or evidence term. That's actually not how the LIGO search pipelines work, though. They're starting to move in that direction, but historically they've been more of a frequentist experiment where you're trying to reject the null hypothesis. So if you've heard, I don't know, you might have done a data analysis course. I've taught data analysis course in this way as well. So you have, in Bayesian inference, you always have to compare different possibilities. Well, unless you're very lucky and you can compute the absolute probability of a particular theory. But normally you wouldn't be able to do that, and you would just have to compare different theories. Another way to do that, another way to do a test for the presence of a signal, for example, is to write down the noise model, run the experiment, and then ask how likely is it that the outcome that I got is under the noise model. So then you compute something like a p-value, which you've probably heard of. So in our case, we have a detection statistic that's called rho, and yeah, it's basically the SNR, okay, rho squared for the shape I've drawn there. So then say in the experiment I observed a value of rho squared here, then the p-value is the area under this curve. And typically if you ask for 5 sigma detection, that means that you're looking for a p-value that's so far out here that the fraction of probability in the tail above that is, what's 5 sigma? I actually don't know. Something like that. Okay, so that's my brief introduction to Bayesian inference. I should point out that in order to do these things, you have to do another integral. This is why I was saying that these methods were not popular until recently, because there's a lot of integration involved. So that integral there, okay, I didn't write the integral. Yeah, there's nothing on the denominator. So that integral is an n-dimensional integral over all of the parameter space. And as I said before, the parameter space for LIGO is like 50 dimensions or something like that. So you're doing a 50-dimensional integral of a function which is, remember, something like e to the minus the sum over detectors times the sum over frequency bins. And that can be 3 for LIGO. Frequency bins is maybe like 10 to the 5-ish. And then you've got your minus a half. Okay. The inner product. Okay, something like that. So, I mean, each of these things costs computational power. And if I'm doing a 50-dimensional integral, I don't want to be evaluating this at every single point on the grid. If I was to do it exhaustively, I'd have 2 to the 30 evaluations of this function. Has anyone worked out what 2 to the 30 is yet? Two to the 10 is a billion. Okay, yeah. So if each of them is, say, 10 milliseconds, right, then how long will it take to exhaustively search this? A billion times 10 milliseconds. It's like 10 million seconds. 10 million seconds, 1 year. So you know, it's feasible, but that's for a cheap model, one that runs in 10 milliseconds per trial. You might want to do something more sophisticated that takes a second per trial, and then you're really out of luck. Well, exactly. You can parallelize it. That might help. Yeah. So the rest of the talk is going to be about how to do that in an efficient kind of way. The workhorse algorithm in all of these problems is called Markov chain Monte Carlo. Have you heard of this before? Yeah, okay. I highly recommend trying to just code up your own version of Markov chain Monte Carlo. It's actually very simple to implement it for an easy problem. And it's instructive because you'll learn a lot of the difficulties along the way. So for like one-dimensional Gaussian, for example, you can see how it works. So Markov chain Monte Carlo. Should explain the name, I guess. So Monte Carlo methods in general refers to the city of Monte Carlo, which is full of casinos. So this is a jokey name that people gave to ways of doing integrals by basically repeatedly throwing the dice and seeing what you got. Markov chain is a particular type of evolution model of a sort of state thing. So you can imagine I'm taking a random steps. So it all comes down to taking random steps around parameter space. So let's go with 2 dimensions to begin with. And say there's some distribution that I want to know about. It looks like that. Then with normal Monte Carlo, I would pick a point, just throw random points all over the space, and if I wanted to know, for example, the expectation of the likelihood, which is the evidence, then it would be something just like the sum of the likelihood at each point divided by n, for example. Now, that's all well and good if you're got a good chance of hitting the sort of near the peak of this distribution. But as I said a minute ago, this distribution occupies 1 part in 2 to the 30 of the parameter space. So just by randomly throwing samples at this thing, it's going to take you a long time to hit the bullseye. So the Markov chain bit is kind of what makes it work. And that means that instead of just doing it completely at random, you start at a certain point and then you make a sort of intelligent guess about where the next step will be. So to do that, you have what's called a proposal distribution. It tells you how I get from point A to point B. So there's a little probability distribution here that says my next step is going to be somewhere around here, and say it's here, for example, that I test. I'll erase the proposal. Then I make this little jump, and I ask, well, what's the likelihood at that new place? So I've got A prime and A as being the new place and the old place. So if the likelihood at the new place is higher than the likelihood at the old place, then I go there. That's fine. That's obviously right, because I want to move towards the peak. So I make another random jump. I'm lucky it goes up. So I keep on making random jumps and tend to walk uphill. So this is a kind of like a search algorithm. It's looking for the peak. But there's another thing. What happens if I make a jump and it's in the other direction, say here, and it's away from the peak? Well, in this case, I have to evaluate the ratio of these two likelihoods. So say it was 5 here and 4 here, then I would have a 80% chance of staying where I am. Wait, is that right? No, I have an 80% chance of making a jump to the new place, because I want to take the ratio of the new likelihood to the old likelihood. So 80% of the time I will move away, and 20% of the time I'll stay where I am. And that's important because it means that you don't get stuck, right? So eventually, if I just went uphill to get there, okay, it's good for finding the peak, but it doesn't tell me what this distribution actually looks like. So it's important that I am able to jump away, make jumps elsewhere, you know, around this space. And eventually, once I've done this for many, many times, I'll find, and you can prove this, and the proof isn't that hard, but I didn't make a slide on it, so I'm not going to do it, that the density of points is proportional to the density of the distribution that you're trying to sample. So you can avoid doing 10 to the 30 random trials and getting 1 in the right place if you actually use the information from the previous point to choose the next one. And that's called a Markov chain. A Markov chain is a sort of transition that looks back 1 step in history. It was invented by a poet or a mathematician who liked poetry. He was trying to come up with a mathematical model for Russian poetry. And he looked at it by analyzing how often one word appeared after the previous word. And you've probably seen these little online things that sort of generate random text fragments. And these are all based on Markov chains. So he had sort of computer-generated Russian poetry. It's just gobbledygook. But out of that came a useful algorithm. So how does it work? Well, I've told you how it works in theory, but here's a movie which maybe helps explain it. So you can see that this is called a Markov chain. It's moving around, it's jumping up and down in this space as time goes by. This is the likelihoods that it's finding. And this is the histogram that you get if you just make the histogram of all the samples up till now. And you can see that at the start, it's jumping around, but it's generally moving up. So there's a little step at the start that's called the burn-in, and that's kind of where it hasn't yet found where the peak is. But once it finds the peak, then it sort of settles down and just oscillates around the peak. And so eventually, it will converge and give you this distribution that you're interested in. So that's how Markov chain Monte Carlo works. Very much so. That's a big problem. That's what I'll talk about in a minute. Well, one of the things I'll talk about in a minute. Do you want a lot of the problems that we have basically boil down to that, because then you know this is a local step, and if the distribution actually has a second peak here that I didn't know about, then it may not ever get there just by doing these little jumps. You can prove that if you wait an infinite amount of time, it will get there, but you don't want to wait an infinite amount of time. So there are a lot of the techniques are in how to actually efficiently explore this space. It's even worse, of course, 2 dimensions, this is bad enough. 50 dimensions, you've got no chance of ever going here in a reasonable amount of time unless you have some clever way of looking for these things. Before we get there, though, the other method that I want to talk about, the other one that we use in LIGO is nested sampling. Oh, sure. Yeah, we check the sort of various convergence diagnostics that you can use. There's no general one, I think, that solves the case, that can tell you for sure that your chain has burned in. But there's a couple that we use. One is that you check that if you take subsamples of your chain, then say you take 100 independent points, that distribution in each of the 100 points is statistically the same, because once it's burned in, it should be. The other one is that you kind of know, there's a rough heuristic that tells you, let me run the movie for a second. Come on. Yeah, the burn-in is just the bit here, so before it's found the right place. So you should really just throw away these samples because it's not going to be representative. The other thing is that if you know the number of dimensions, then you know roughly what the distribution of the likelihood should be. In the case of Gaussian, is that it's a sort of backwards-looking chi-squared distribution, where the scale length here is the number of dimensions over 2. So you can check and see whether your highest probability sample, your highest likelihood sample, is more than n over 2 times the likelihood of your average, say here. Okay, maybe it should be this one. So that's the other one that we use. I think there are a few more. Ben Farr will probably have some more tricks up his sleeve. Yeah, yeah. Yeah, yeah. That helps a lot. If you know that in advance, then it can save you having to do the burn-in, which can take quite a long time sometimes. But then, of course, you need to know that. So sometimes you do know that because there are tricks you can do to maximize, but often you'll just have to let it run and see how it ends up. I don't have a slide on it. I was going to sort of play it by ear and see what comes up, so I'll put it on my list. Yeah. So I'll talk about. I'll mention that now. So he's talking about thinning the chain. So if you can see in the diagram that because it's a Markov chain, it looks back one sample into the past, and you have a little proposal distribution around that. Then the next sample is going to be close to the previous one. So there's a sort of correlation between samples in the chain, as you know, between one sample and the next one as you go along. And people often say, well, I've got 1,000 samples from this distribution. That means that you know, my accuracy, for example, in estimating some Monte Carlo integration error goes like the square root of n, or 1 over the square root of n. So if I take 1,000 samples, I would expect to get to something like what is it? What's the square root of 0.3? No, 3% accuracy. Is that right? Yeah. But if these samples are correlated, then I'm actually not going to achieve that because I don't have the same sort of exploration as I would if I really had 1,000 what we call independent samples. So people will often thin this chain. So that means that they will only take, say, every 10th or every 100th sample. And there the idea is that because you're waiting a longer time, the correlation dies away. And the amount that it dies away as a function of iteration is the autocorrelation function of the sampler, which usually looks like something like that. So what we do for LIGO is that we wait until this thing drops below, I think, 5%. It's one of the tuning options in the code, but I think it's 5%. So if that was typically something like 1,000 samples to wait until the correlation timescale is over, then it means that we only get to keep every 1 out of 1,000 samples from our chain. That's good. I mean, it's good practice to do that because then your samples really are independent and you won't get misled by Monte Carlo errors. But actually, and statisticians will always point this out, if you have truly a converged Markov chain, then any estimator that you have based on these samples will be unbiased nonetheless, as long as you've got a sufficient amount of them. Because on the average, you know, you're still exploring the whole space. Unbiased is not the same thing as kind of having the right variance, I guess. Sorry, I'm just going to get some water. Yeah. 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 It depends what you want to do. So one of the tests that we do to check that our code is working properly is what's called a PP plot. You know this? Yeah. So if we have, sorry, it's not the PP plotting thing, it was a KS test. So we can do a test. One of the tests that we do on our code is that we give it a known distribution. We give it a known distribution and tell it to sample it. And then you can do a statistical test to check whether the sampler has found the right thing. So I can plot the cumulative distribution like that for an analytic function. And then the version from the samples that are output might look something like that. And then there's a Kolmogorov-Smirnov test that basically works out what's the maximum difference between the empirical distribution and the analytic distribution. And there's a KS test statistic that depends on the number of samples in the sample distribution. And it depends on the number of independent samples in the sample distribution. So if you don't thin, then this will mislead you into thinking that you're failing your KS test. So that was puzzling us for a while until we realized that we always had to thin. So we always do thin. All of the results in LIGO publications are based on thin samples that are independent to avoid this problem. When we release them to the public, I expect people will have a field day looking for bugs in our code. Okay, let's move on. Nested sampling is the other algorithm that we use. It's my favorite. I like it because it makes nice movies, but also it gives you the evidence out. So I said before that when you're doing model selection, you want to know this normalization constant for the posterior distribution. But, so that integral there, in fact, is the one I wrote down, and I managed to write it down correctly in this case. Good. So this is a kind of more recent method. It was only 2004 that this guy Skilling public, although I think he'd been using it before. He's a strange, I don't know, have you ever met him? No. He lives off in the west coast of Ireland, like away from everywhere, and he makes his money by doing data analysis for governments. But he seems to be some kind of genius because he just throws out these algorithms every once in a while that tend to blow everyone else out the water. But he leaves the details to others to implement them. So there's always a little bit he doesn't tell you. Anyway, this is one that he put out in 2004, and people have been improving on it since then. So there's all kinds of variants that you can find, and I've put a list at the end of the talk that shows you where to get a few of them. The idea here is that instead of doing a Markov chain to explore the distribution, you take your probability distribution like this and map it into another space. In particular, imagine that you have the probability distribution represented by a set of contours. Now, if you know the area inside these contours, inside each of these contours, is, say, this one is 80% of the volume of the box, and then the one inside that is 80% of the volume of that one, and then the next one inside is 80% of the volume of that one, for example. You see that the subsequent volume that goes down every time is going to be 0.8 to the power of n, where n is the number of the iteration. Of course, this is a geometric series, so I'm trying to narrow myself in on something that's 2 to the power of 30, right? So if this is 0.5, then n would only have to be 30 before I get to the right answer. So I could find the peak in 30 iterations if I can get these contours right. So this is guaranteed to always converge, which is a really nice feature that it will eventually terminate. For MCMC, you can keep running it forever. You'll get more samples out, but you never, well, you have convergence tests to check whether you really have the result that you're after. But you know, you can just keep going. It's up to you to decide when to stop. For nested sampling, the algorithm itself eventually stop because eventually you run out of likelihood. You reach the peak. So this x variable here, you've got a mapping from a sort of high-dimensional parameter space to a one-dimensional parameter x, which is the fraction of the volume of the space that's enclosed by each contour. And so you can convert the integral over n dimensions here to a one-dimensional integral over x, which is kind of black magic, if you ask me. It doesn't matter. All that matters is the volume enclosed by these contours. The contours don't have to be connected. They can be multiple islands. The difficulty is in actually finding what the contours are, which is probably the next bit. But that's the beauty of this method, is that it is applicable to any probability distribution, even ones that are non-continuous, in fact. So, for example, the skilling paper shows you. There's two papers. The first one is kind of short-ish, but quite, slightly more intuitive. And the next one is a bit. Yeah, there's a couple. It's nice because there is another algorithm which I probably should have mentioned called thermodynamic integration that tries to get this evidence number. And it can fail when you have what's a phase transition. So that's like a point of inflection in your curve here, basically. Because then you have to kind of sample very large gradients or very small gradients, depending on how you think of it. So that can fail in certain cases. Admittedly, they're not the cases that we're interested in, but apparently that can happen. So this gets around that. Yeah. Just talk. Oh yes, that's the bit I should have explained. So yeah, the problem then becomes, how do I draw the contours without mapping out the entire space, right? Because I would think that I would have to actually make the map and then work out where the contour is to do that. That's where the trick is. This is a really nice feature, is that if I have, say I've got this curve like that. That's this curve there. Now, I don't just have one point. I have, say, 1,000 points that all lie to the left of this line. And they're uniformly drawn from the prior. That means uniform in the volume in most cases. Okay? So if I have lots of points that are uniformly drawn inside one of these contours, then I can ask, what is the volume enclosed by the rightmost or the worst point, like the next contour? Each has, we know the likelihood value for it, so we know the value of the contour in the y-axis, and we know that because they're uniformly drawn inside the volume, that it must occupy a certain fraction of the prior, and that the distribution for that is a beta distribution that's very, very peaked towards 1 when n is large. So the mean. So this is the probability of the fraction, I'll call it f. And this is f. And that's the fraction enclosed by the last contour, the outermost contour of the total. So that's like when I do f to the, when I said 0.8 to the n, then f is 0.8. And that would be the case if I had something like 5 live points. Now, the error also scales like the inverse of the number of live points, as they call them. So in order to get an accurate integral, you need to use lots of points. And typically we use about 1,000 in our actual analysis. So the more, if I have a small number of points, the distribution looks like that. And as I put more and more points in, it gets tighter and tighter up against 1. So the relative fraction gets bigger, but the error also gets smaller. So there's islands. Well, it's the same problem as MCMC. Like if you got more islands, then you still need to be able to make jumps between islands in order to find them. So you don't get around the problem so easily. You know, it doesn't solve that problem, but it gives you the evidence integral, and it's quite a nice method. Yeah, you have to start off with the entire prior, in fact. You have to. It depends on specifically the information in the data. So we get back to this Shannon entropy and so on again. So in particular, say that this is the peak, right? This is log of x, and this is the likelihood here. Then it takes me roughly, the information is something like the number of steps it takes me to get to the peak. So it could be, is that right? Yeah, if I shrink my volume, okay, so after I've done, right, say I have, let me do it a little bit. N is the number of live points, okay? So forget this for a second. Then after I've taken n steps, then the volume is a function of n. Okay, so say x, because that's the expression I'm doing. X as a function of n is roughly equal to e to the minus, x as a function of I is roughly equal to e to the minus I over n, just because the geometric series becomes an exponent like that. So after I've done, say, 30 times n steps, and then I find the peak, then it means that the peak is enclosed in a volume that's roughly e to the minus 30, for example, compared to the prior. So the relative compression is e to the minus 30, and e to the minus 30 is roughly 2 to the minus 60. So in this case, it would be about 60 bits of information. So you can get the number. So I say that the information here tells me the thing in the exponent, and that tells me how long I have to wait before I get to the end. And that tells you how long it takes to run the algorithm. Yeah. If you make your prior bigger by a factor of 100, then it will take log to the base number of live points of yeah, that's good. The geometric series is the key to it all. For which integrators? Yeah, well, there's the thermodynamic integration as well, which we could have used. Yeah. I can't remember how the computational cost of the thermodynamic integration goes. I don't know if anyone knows. Yeah. Yeah. There are sort of rules of thumb to set the temperature scales. I actually have a slide on that later when I talk about parallel tempering for MCMC. But that's, yeah, there are other algorithms, but I like this one. It's easy to code, and you can do different tricks of, you still have the problem of jumping between islands, right? So people have solved this in different ways. You've probably heard of multi-nest, and that's one that attempts to identify the islands and then subdivides the space so that it concentrates on each island one at a time. Mm. Yeah, I mean, the only drawback to this is that, at least when you do it naively, say I have two models, one that has 5 signals and one that has 6 signals, then I would have to run the algorithm twice, once with n equals 5 and once with n equals 6. There's nothing in what I've written that prevents you from doing that. So in that case, you're working on the product space of all the different possible models. But there's nothing in this description of the prior and the geometric shrinkage that depends on the number of dimensions, you know? So that, in principle, it should still work. But I've not actually tried it, so I don't know anyone who has, but Brendan Brewer claims that it works. So, oh yeah? Okay. Yeah, the Cambridge group, which Skilling I think was affiliated to in some way, were one of the ones that pioneered these methods. So they also have polychord as a sort of variant of nested sampling, multi-nest. Bambi was the one that Philip Graf was working on. So they're all based on this idea, and what differs is how they divide up the space and how they get between islands and so on. There are other things you could do. I think one that I'm interested in is changing the number of life points as a function of the parameter, because you don't necessarily have to keep that a constant. You know how they shrink as a function of the life points. So if there are hard parts of the parameter space and bad and easy parts, then you can change it adaptively as you go along. Oh, okay. Yeah, I would love to. It's been a while since I actually looked at any of that, because I did it with Lisa. I actually have slides on that later. I'm going to run out of time, rather surprisingly. So let's press on. This is all weird, high-dimensional stuff, so I always like to provide a movie. So this is how nested sampling works. So the red are the live points, and blue are the dead points. So that's the ones that have already been eliminated. And you can see that as iteration goes on, it's sampling, it's wandering around. This is all different projections of the parameter space. And that's the curve shrinking geometrically as the likelihood goes up. And you can see that after about 30,000 iterations, it's narrowed in on the place where there's a peak. And you can see it also lets you read out the structure of the likelihood function as a function of likelihood, which is nice. So you can sort of see where the secondary islands in the sky here are. And this tells you the degeneracy between the phase and the polarization angle in this case. But there are all these kind of things. You can make nice plots and movies, and it sort of gives you a good feel for your problem, because you get to see it at all scales of likelihood. Here's another example just for the time delay for LIGO. It's nice you sort of see the structure of that sky ring that you were talking about earlier. There's the ring, and you see the symmetry in the ring is broken at higher likelihood values. You can project it into time delay space, and you can see that what is an annoying ring shape is actually more like a line. This is in seconds. Python. Yeah, so that's delay between Hanford and Livingston, delay between Livingston and Virgo, Hanford, Virgo, Hanford, yeah, you get the idea. So this kind of shows you that what is a complicated ring structure on the sky is something a bit more simple in the time delay space. In particular, it's dominated by Hanford and Livingston usually, because they're the more sensitive ones. Yeah. Yeah, I mean the whole prior in this case, you can see where it lives. Outside of these are unphysical time delays, so it doesn't even allow them at the start. It's a flat prior on the sphere. So you can see, let me run it again. You can sort of, I don't know if I can pause the movie. Does it let me do that? Yeah, so that's the shape of the flat prior, and sky position is clustered somewhat around the edge. Okay. So before we go further, LAL inference is the name of the code that we use for LIGO, and it's kind of the result of lots of people's hard work over about a decade of developing these algorithms up from the very basic sort of 4-parameter in spiral. As you make the problem more complicated, it becomes more difficult, so you have to tackle it bit by bit. So over the course of all this time, we tried different methods, and eventually we sort of combined forces into the parameter estimation group in LIGO, which works on this LAL inference code. You can download it. It's good for gravitational waves, for ground-based, but it's a bit clunky for other problems, so we'll probably rewrite it in Python, make it easier to use. Yeah, so we do all these kind of convergence checks and cross comparisons and so on. So some convergence checks that we do are just to run the different samplers. They're independently implemented codes, so you know that if they find the right answer, then the sampling is not going to be biased. As I said before, we check against known likelihood functions and then do the KS test to make sure that things work okay. Another good one is this PP test, where you have to check that, say I do 100 injections of fake signals that's drawn from the prior, then if the code is unbiased and the probability estimates are well calibrated, then 5% of the time the true value should be within 5% of the probability, and 50% of the time within 50% of the probability, 90% of the time within 90% of the probability. So that's checking the frequentist way that your Bayesian probabilities are really what you think they are. So we do these things, and then you plot the number of things within a contour against the value of the probability contour. And if it's correct, then it should be a diagonal line. Okay, so we've not actually got onto these tricks yet that I wanted to get to. So just to motivate that, computational cost for the nested sampling, for example, you've got your n live points, roughly 30 bits of information. Each of those requires a little MCMC chain to make the next point. Then for each of those, you calculate the likelihood, and then you do that for each interferometer. And for that, you have to calculate the template. And that in itself is the most expensive step. So you're multiplying, 10,000 by 1,000 by 3 by the cost of a template calculation. So you really want to make this as fast as possible to begin with. So that's why we value these frequency domain models rather than numerical relativity or very expensive time domain models. And we like to avoid doing FFTs to make it faster. And then we use various tricks to make this shorter. So as I said before, the autocorrelation timescale for MCMC, and you want to only use samples after that autocorrelation timescale has elapsed. And so the shorter you can make that timescale, the more efficient your algorithm is going to be overall, both for the MCMC, where you get more effective samples, and for nested sampling, where you can make these little subchains shorter. By the way, this is also true for multi-nest and things like that, where you don't have a subchain, you don't have an MCMC chain to make the next point, but you still have an ellipsoid that you have to sample with a certain efficiency. And typically I find that the number of points in my MCMC chain is about the same as the efficiency of the multi-nest things. So we always thought multi-ness should be better, but it doesn't seem to actually improve. It's good for dividing up the islands, though. Okay. I'm going to skip over a couple of things. Well, maybe I shouldn't skip it. A trick that we play is that this is adaptive, the length of these chains, depending on the current autocorrelation timescale. So that's the first trick for nested sampling. So you can sort of have a self-tuning code that examines its own efficiency as it goes along and adjusts how fast and slow it can make, how long it makes its chain. Likewise for this, you don't need to do it for every sample in the chain. If you know that because you actually sample the prior in nested sampling, it means that most of the time you will accept it, but occasionally you will reject it. So you need to, if you do the prior check first and you find that you reject, it means that you don't even need to compute the likelihood. So you can get a vast speed up that way. And then the code is self-tuning so that the fraction of the time it actually bothers to check the likelihood depends on how hard a time it is having sampling within the contour. So if you take these two things together, you find that overall the number of likelihood evaluations, which would naively be 5,000 times whatever is on the x-axis. So this is like if you had a fixed and sufficient number, is now reduced down to only what's underneath the green curve. So it's probably a factor of 20 speed up for these little tricks. That's all described in the Lal inference paper. Why is this going slowly? Yeah, the other thing, because you mentioned yesterday that you do some marginalization over some of your parameters. We do the same thing over the phase parameter signal, which is one that's very easy to get rid of for the L=2 mode only, because there you know how the likelihood goes. So basically what happens, if I write the gravitational wave signal in the frequency domain, it'll look like some template times e to the I phi. And this phase of the wave is something that we don't really care about that much because it's not of physical interest. So when you put that in your likelihood, you get terms that go like this. Okay, because you can take this out. It just multiplies the wave overall. So you can take it out of the inner product. And then what you do is you integrate the likelihood over the phase parameter, and you get this Bessel function form of the likelihood there. That helps a lot because this parameter is degenerate with the polarization angle for signals that have a face-on inclination. And that degeneracy is very sharp because you saw that movie where those stripes, those diagonal stripes, they're quite difficult to sample because it's highly correlated. Now, if you know the correlation, then you can sample in that direction, but it depends on whether it's face on or face away or any in between. It has a superposition of stripes going different directions. So by eliminating one of those dimensions, you get rid of the stripes. It just becomes a nice flat distribution. So it improves the overall efficiency more than you would think just by eliminating a dimension. I was going to ask you what you're marginalizing over, but I'll find out later. I think the B statistic actually does more than this because they marginalize over the other extrinsic parameters. Yeah, we can talk about it tomorrow. Okay. Oh, right, okay. Was it? I thought I invented that. Oh, wow. Typical. I can parallelize nested sampling, so I don't have to run one chain with 1,000 life points, I can run 5 chains with 200 life points. So I can speed it up by a factor of 5 without losing any resolution. Eventually that breaks down. I can't speed it up by a factor of 1,000 because the code needs to have several, well, at least 50 life points, otherwise it will start missing the islands in our experience. So there's tricks like that as well. Yeah, yeah, but you don't want all of them to miss. Well, I mean, it's basically a trade-off. You can see here the difference in the results that you get. One chain with 1,024 points, 16 chains with 64 points, 8 chains with 128 points. You basically get the same results, but I guess 16 chains with 64 points is green. It's actually not bad in this case. But if you go much beyond that, then it stops becoming so good. It gets a bit more noisy as well, because some of the chains have missed and you have to throw them away. Okay, possible other speed improvements that we've not really investigated yet. The adaptive number of points I was talking about. Parallelization, sort of internal level. This is an old slide. This has actually now been implemented in the Python version of this code, so you can download that. Other algorithms, other versions of nested sampling, including diffusive nested sampling, are allegedly more efficient. So I've got a link to that in the last slide. More efficient jump proposals, using your knowledge of the problem to speed things up. By knowing, if you know where the islands are, if you know what the separation in the islands is, for example, then you can preferentially try and make jumps of that size, and it means that you're more likely to hop between the islands. Now, you don't always know what the separation of the islands is, so there are other tricks you can do using the information you have to try and make intelligent guesses. And then there are things about templates, for example. Other analytic marginalization. I don't think it's possible to do it analytically, but you could probably do something. And there was a paper by the Hanover group, Badri and Reinhardt recently. Yeah, that did this. So they managed to evaluate the B statistic. More scope for further improvements, but it's a matter of taking the time and the experimentation to do things with them. So I'm nearly out of time. Before we end, I want to just go through a few ways of speeding up MCMC as well. Ensemble samplers, reparameterization, parallel tempering. Then I'll talk about changing the number of dimensions. That's this Lisa type problem. We don't know the number of white dwarf binaries. Delayed rejection is another good way of doing island hopping. Hamiltonian Monte Carlo, I didn't get around to writing a slide about, sorry. Ensemble samplers is the first one. So this is a nice trick that's used now in a couple of off-the-shelf MCMC codes that you can download. The MC package that's very popular uses this, but it wasn't invented by them. It was invented by Goodman and Weir in 2009. So the way that this works is that instead of just having one point that you're jumping around in the space, you can have, say, 1,000, and then because they're already sampled from the distribution that you're interested in, you can use the fact that you've got all these points in the space to preferentially make intelligent jumps. And there's two types that they talk about in the paper, the Goodman and Weir paper. There's also one called differential evolution that's really a sort of a version of this that only includes 2 points. The first one is a stretch move. So here, say I start at this point, and I want to find a good place to go. Well, I've got all these other points around, and I know that they are in good positions. So I basically want to move along this ray between the current position and one of the other points. And I just pick the scale of the jump by a certain amount. So I sort of move in this direction around that point. And then there's some tricks you need to know about making this reversible in order to prove that it converges properly, but I won't get into that today. You can read the paper for more information. The other one is the walk move. So the idea here is that you're not moving this particular point itself. Sorry, that's not the, this is the current point that's evolving, and that's the target one. So here, this is the current point, and this is the jump. And the size of the jump, in this case, you just pick a random collection of the other points and sort of work out the geometric center of them. And you can prove that the variance of this geometric center point from one of the corners, that distribution is equal to the overall distribution of the points. So even if you don't know analytically what the structure of the parameter space is, you can still get it by using the sort of points that you have, the information from the chain. So this is a way of kind of learning on the fly what your distribution looks like. And that's used in the nested sampling code as well, because there you've got all these points anyway, so you may as well use them to do these kind of walks. So that helps. Oh yeah. Another one is reparameterization. So you might write down your problem in one set of variables, say mass 1 and mass 2. Those are the ones that you care about. But you find that results give you posterior distributions that look like this. So each of these here is one of the probability distributions. It's basically extremely thin in one direction and very long in another direction. So if you know that it's going to be preferentially thin in one dimension and thick in another one, then you just change variables to turn this into a kind of more separable Gaussian distribution. In our case, the chirp mass is the parameter that we use that describes, this direction, and the mass ratio is the parameter that describes where you are in this direction. And you do the same thing with the sky ring. So one of the other tricks that we have is if I have Hanford here and Livingston here, and I get a trigger, then I know what the time delay is at any one point, and that gives me this ring thing. So the ring tends to be a point, of constant time delay. That's not very good. Yeah, so the ring of constant time delay corresponds to an angle, a cone with a constant angle between the vector of joining the two detectors and the sky. So if I know where my detectors are, which I do because they're on Earth and we know where they are, then I can choose, instead of having my variables, so the variables here would be the sky coordinates, that's the North Pole, and then I've got the right ascension and the declination. So this ring is not, it's going to be a horrible function of declination and right ascension. But if I change my North Pole to point along the vector between the detectors, you can see that this now becomes a nice separable in theta and, well, the other parameter is kind of the projection onto this part here. So that's another reparameterization that vastly helps speed up the sky localization part of our problem. Another one is parallel tempering. So if you've got these islands, that's basically what a lot of this comes down to, is hopping between islands. That can happen when your likelihood has multiple strong peaks, and also if the likelihood itself is just very, very peaked. Then it's difficult to land the point in that particular space. You know, say it looks like that, then the chances of picking a random point that goes in here are very, very small. But you can take this likelihood function and raise it to the power of 1 over a temperature. And this is exactly like you know, your partition function in thermodynamics. So a lot of these techniques are inspired by thermodynamics because they're very related. And that will take these sharp peaks and smooth them out, reducing the contrast of the likelihood function. And so it's much easier to walk around and sample this red distribution than it is to sample the blue distribution. So you have chains that are running at different temperatures in parallel. You can implement them in different CPUs to speed things up that way as well. And every once in a while, you try and make a swap between chains with adjacent temperatures. And then you have a certain rule similar to the acceptance probability in the Metropolis-Hastings algorithm. For doing that, that guarantees that your samples will still converge on the target distribution. And you can see, here's a paper by Will Veitch, who's a PhD student, who worked out a nice way. So normally you have to choose where you want the temperatures to be. Will worked out a method of adapting the temperatures themselves to improve the efficiency of the algorithm, targeting a particular acceptance ratio of 0.5. You can see the code as time goes on, it's sort of moving these temperatures around, learning the structure of the likelihood function, and so that they all are performing with maximal efficiency once it's all converged. So that one might be useful. I don't know if you have seen that in the PTA code, for example. You could take the prescription from there. That could quite possibly speed things up. So the last thing I want to talk about is trans-dimensional Metropolis-Hastings, which is basically where you don't know the dimensionality of your parameter space. So you want to allow that to vary along with the parameters themselves. So that kind of situation arises in the analysis of LISA data, where you're looking for these white dwarf binaries that are a confusion noise. But you don't know how many of the binaries there are in the data to begin with. So one thing you could do is you could run the evidence calculation and vary n, but the number of binaries that are resolvable could be like 10 to the 5, 10 to the 6. So you don't want to have to run 10 to the 6 different versions of the code just to find out how many binaries you have, which will not be determined uniquely anyway. You'll get a probability density for the number along with the parameters of the sources. So this method allows you to run Markov chain Monte Carlo, but making steps between models of different dimensionality. So in this case, it's important in particular that when you make a move between a model with n and a model with n plus 1, obviously the volume in the n plus 1 dimensional space is spread out further than it is in the n dimensional space. So there's a sort of Jacobian factor associated with the densities, and that comes into the transition as well. The version that we used in the LISA had 2 different types of transdimensional steps, in addition to lots of these tricky steps as well. Birth and death and split and merge. So birth and death is where you basically say, I've got, the birth move is when you pick a new signal and add it to the current collection. And death is just when you pick one at random of your current ones and remove it. So that's quite an easy one to add into your code. It's not very efficient though, because you don't really know where to put your new things unless you make some intelligent guess. So again, you have to sort of by hand tell it some useful heuristic for proposing new signals. The other one, split and merge, is a bit more automatic. So here you have, say, you're looking in the frequency domain. A white dwarf binary is basically a peak. But often what you'll find is that there are two white dwarf binaries with nearly equal frequency, and then you can't quite tell them apart, or whether it's one binary with twice the amplitude or two binaries with half the amplitude and just very close to each other in frequency. So you make a jump that takes that one peak and splits it into two with a very small perturbation in the frequency and with the same total amplitude. So that tends to be quite good because it has a higher acceptance ratio. It's more likely to succeed, and it will let you, resolve binaries that are very, very close together in frequency. Likewise, you want to be able to go backwards, so you can take two random binaries and try and merge them together into a single peak with the mean frequency and the same total power. I never tried it with more than two. I mean, a split into three, you could say, is sort of doing this twice. So, you could try. I think so. We were doing this like in 2007, and we hadn't used any of the ensemble methods before up to that point because they hadn't really been invented yet. So I think these things are historical, but they could be made a lot more efficient by using some of the ensemble tricks to guide your steps. So when we start getting the Lisa data challenges going again, assuming Neil hasn't already solved everything, then we could try doing this. I think he probably has solved this problem already. I mean, he claims he has, so I don't know if it's worth putting a lot of effort into that. But it does work. So here's an example. It's fully, it's just MCMC all the way through. You don't have to do any initial scanning or anything like that. So here's a case where we had 100 signals in the data. They weren't all, resolvable. Some of them were quiet as well, but the code sort of does a good job of saying there are roughly 195 here. And we also estimate the variance of the noise as well. So as the number of sources increases, those take power out of the noise, and then the remaining power is allocated to the noise model. So this is our estimate of the noise level as a function of the number of sources, and you can see the true values where there's 100 sources and the noise is small, but there's not very many samples that get there because it's actually difficult to resolve them all. Anyway, that's all in this paper if you want to have a look. It tells you about the moves as well. I'm about to run out of time, so I'm not going to talk about delayed rejection, other than that it's a way of doing island hopping. It was invented by Green, I think. Oh wait, it should be down here. Yeah, Green and Mira. 2001, so we tried it around that sort of 2004, 2005 time when we were doing Lisa problems. I think it's gone a bit out of fashion, but we did apply it with success to the binary problem with Miguel Trias, who's a student at the Balearic Islands. So there's this paper here. If you want to know more about that, I think you can just go and look that one up on your own. But the idea is that, of course, it's good for island hopping, because it means that if you try and do an island hop, but you land in the wings of the island instead of on the peak, it doesn't immediately go back to where you were. It lets you sort of explore the island a little bit before deciding whether to stay or not. And there's the autocorrelation times that you get from the reversible jump versus the standard method. Yeah. So we didn't really combine this with the other one. Although the other one did have reversible jump moves in it, it didn't have this. Actually, this is the only paper that we ever tried to publish in a stats journal, because we invented the original reversible jump from Green and Mira was just you do it once and then it lets you delay it by one time. But you can apply a recurrence relation to do this an infinite number of times in theory, but in practice you don't want to go forever. So we derived the right properties for the reversible jumping with lots and lots of steps. Stats Journal hated it because we didn't use all the right formalism. We wrote it as physicists, so they never accepted the paper. But it's sitting in the archive. It actually has a few citations from other people And I occasionally get sent articles by that journal to review. So even though they didn't accept our paper, they accept us as referees. I think that's a bit cheeky. Okay, so I didn't get around to doing Hamiltonian Monte Carlo, but that is a very powerful technique for exploring very high dimensional parameter spaces, where a lot of these other methods don't work. So if you're going up to the thousands of dimensions or more, then you might want to look into that. Adaptive jumping is another one that's a little bit redundant given the ensemble methods, I would say, but people do still use it. And then I heard mention of this Riemannian MCMC that I can't remember how it works, but I think it's some kind of hybrid of Hamiltonian and Riemannian machine learning, possibly, or manifold learning, or whatever it's called. Here's a few things. If you don't care about any of these details, but you have a model that you want to try and fit, then you can download one of these off-the-shelf codes and give it your own likelihood function and just let it go. MC is very popular. It's Dan Foreman-Mackey's code that uses the ensemble sampling methods. Combine is Ben Farr's and Will Farr's code, and it uses a kind of fit to the likelihood based on a decomposition into Gaussians. It's a bit like multinest. I should have also put multinest here as well, actually. So you'll have to Google for that. I don't think it's on GitHub. There's diffusive nested sampling by Brendan Brewer. That's like an advanced version of nested sampling that lets you, it's sort of a hybrid between nested sampling and MCMC. It's supposed to be several times more efficient than vanilla nested sampling. And then there's my code here with Walter. It's like a parallelized version of nested sampling in Python. That's only just gone up, so if you are trying it out and you find any problems, then let me know. I'll be happy to help. Yeah, the other yeah. I'll check it out. Yeah, I was always tempted just to add the kind of clustering step to the nested sampling code, but it was a pain in C, actually, to do the k-means clustering. They're not MPI. MC uses Python pools. Combine, I think, uses Python pools as well. I'm not sure about dnest4. I know it's parallel. It may use MPI. And this one just uses Python pools as well. So, although I hear tell that there's a thing called MPI4Pi that lets you basically take a standard parallel Python code and convert it to an MPI code. I've not tried it out yet, though. Okay, that's the end of the show. So it's time for lunch. But if you want to know more, then oh.